When we were talking about importance sampling before, one thing we were implicitly assuming was that not only were we able to draw efficiently, that we were able to sample efficiently from this proposal distribution Q, but we were also sort of implicitly assuming that we could efficiently evaluate f and w, this importance weight function, that we could efficiently evaluate these functions at those points that we drew. And one thing that can happen is that's not possible. So it can happen that, in particular, that you can't efficiently compute these importance weights. And the reason why that usually happens is because you only know the distribution either p and or q up to a normalization constant, up to a constant of proportionality. So in this video, we'll talk about importance sampling when you don't have the normalizing constants. So we're going to assume that we know p and q up to a normalizing constant. So let's say that p of x equals p tilde of x, and here p is a PDF like before. It's equal to p tilde of x, some function p tilde of x, divided by a positive constant zp. This is the normalizing constant. And the same thing for q of x. So if you happen to not know these normalizing constants, is it still possible to do importance sampling? So we're going to take a look at that in this video. Now, the reason why this situation is a real situation and can occur is that, even though mathematically speaking, once we know q tilde, then we can just integrate it over all the values of x, and so the integral of q tilde of x equals zp, because the integral of q has to be 1, or sorry, zq, and the same thing for and that, of course, that has to be some. We want zq and zp to be positive numbers. So mathematically speaking, you can always recover these normalizing constants, but these integrals might be extraordinarily difficult to actually carry out. So this situation occurs with quite some frequency. So let's see what we can do here. What can we do? Well, let's write down, just what this expectation is, and we'll see what happens if we try to do importance sampling. So this is integral f of x px. I'll drop the dx for now. It's integrating over dx. And now if we multiply and divide by q of x, what happens? Let's just do it and see what happens. Well, we don't know these, so let's plug in what we do know. We get f of x p tilde of x over q tilde of x. Then we have to put in their normalizing constants, zq over zp, that one with that one, and that one with that one. And let's leave q here. So we'll be assuming that we can still draw samples efficiently from q, but that we just can't evaluate p and q efficiently. So let's we can do a Monte Carlo approximation, assuming, we're assuming here, maybe I should write that. So, and assume this, and can sample efficiently from q. And we can evaluate p tilde and q tilde. I've said all that. Okay, I've said it enough times. So let's write down what the Monte Carlo approximation here is. It's zq over pq comes out. That's just a constant. And so this is 1 over n, sum as I goes from 1 to n. 1 to n. And now what do we have? We have f of xi times, let's call it, it's going to be p tilde of xi over q tilde of xi. Let's call that w tilde of xi. So here, w tilde of x is this sort of in some sense, it's the unnormalized importance weight. And we can evaluate this because we can evaluate, by assumption, we can evaluate p tilde and q tilde efficiently. But what about these normalizing constants? That was the whole point. We didn't know the normalizing constants. So what are we going to do? How can we figure out what this ratio is? Well, let's write down what it is. Maybe we can do something. Let's write down, actually, let's flip it. I sort of know what's going to happen here. So let's flip it. It's going to be a little easier. If we do zp over zq, and let's expand what zp is. Zp, well, here it is. It's equal to the integral of p tilde of x dx. And we want to somehow get rid of this zq now, right? Because we don't know what that is. So zq is, well, we can use this definition here, q tilde. So it's zq is q tilde over q. So we could put p tilde q of x over q tilde of x. And now things are looking pretty good for a Monte Carlo estimation of this, right? Because we can draw samples from Q. In fact, we've already done it for this part. We can draw samples from Q, and so this is, we can do a Monte Carlo approximation of this, and it's just P tilde of xi over Q tilde of xi, which is W tilde of xi. So we can use the exact same xi. So here, this was where xi, x1 through xn are distributed according to q. And we can use the same xi's here. So if we plug this in, plug this approximation in, this green part, let's say that was, let's say this was just an aside, and if we continue the green line, we can approximate this further by, it's approximated by this divided by 1 over this, which is zp over zq. So it's 1 over n, sum as I goes from 1 to n, f of xi, w tilde xi, divided by zp over zq, which is this, w tilde xi. And let's rewrite this. Let's pull together, let's move this denominator. Let's divide w tilde by the denominator. And we'll call that, let's put it in front. Let's call that w hat xi. And so here w hat. So let's write down what we got. We got the following approximation. Now this was 2 Monte Carlo approximations. This was the first one for this integral, and then we had yet another Monte Carlo approximation. Actually, it was they're both Monte Carlo approximations. Another approximation for this ratio of normalizing constants. And so we get that when we don't know the normalizing constants, we can still do importance sampling, and we have the following approximation, where x1 through n is distributed according to q, and w hat of x equals, what is it? It's w tilde of x, or actually I guess we just want w hat of xi equals w tilde of xi divided by the average, 1 over n, W tilde xi. And W tilde of xi, of course, maybe I'll go ahead and write it here, get it all together. Or we can just say W tilde of x is P tilde of x divided by Q tilde of x. Okay, that probably wasn't necessary to write all that, but just to be perfectly clear, this is important sampling when we don't know the normalizing constants. Now you can note that this formula, there's a strong similarity. You can sort of remember this maybe by noting the similarity with the original importance sampling formula here. It was just the same, except now we have when we don't know the normalizing constants, we have to, in some sense, estimate these importance weights. So we had the W hat down below. So we had the W hat, and that W hat is in some sense an estimator of the importance weights, W. So that's important sampling without normalizing constants. And just remember, keep in mind that there was no free lunch here. We were able to still do this, but we had to make two approximations. And so, we had the first approximation, and we had the approximation to the normalizing constants. And so this is this in general, it's not going to perform as well as just the standard importance sampling when we do know P, when we can evaluate P and Q efficiently.